Welcome. I want to talk today about a technique called bag of visual words, which is an approach for finding similar images, for example, in a database of images. And that's a frequently used problem in computer vision, photogrammetry, or robotics when you want to make data associations. You, for example, want to find two images of the same place, to do place recognition. Or you want to find similar images in a database given a query image. These are all tasks where you want to look for similar images, similar data items. And bag of words is a popular technique that can be used in order to do that. So as a preparation for this lecture, you may want to start this 5-minute summary of this whole lecture explaining bag of visual words very briefly. If not, just lean back and enjoy what I'm going to present here. So what's the bag of visual words? It's a technique that can be used for finding similar images in a database, either images among each other in the database or with respect to a given query image. So let's say you put into a database a large set of images and you want to find an image in your database that is similar to one query image. And then the question is, how can you search for that? And bag of visual words gives you a possibility so that you can put in this image as your search query and bring back or return images that look similar to the one you queried for. That's similar to what's, let's say, Google image search, for example, where you can drag and drop an image to the search window and it will return you similar images. And bag of words is one approach to do that. Additionally, bag of words also provides a quite compact representation of the image, so that in the end you do not actually need to store the image. It's sufficient to store a compact representation, which, as we will see, will just be an histogram of certain feature occurrences, and you can do all the comparisons based on those histograms. So you may wonder about the word bag of words. Why word? And the reason for this is that this is a technique which stems from the text mining community. So if you have a large number of text documents and you want to find text documents that are similar to a query document, or you want to group those documents into different types of documents, let's say legal documents, reports with respect to trade aspects, or papers from robotics, or papers from a different discipline. So whatever it is, you want to group those documents, or you want to look for similar documents. So it's, as you know, a common technique or a common problem in libraries or in searching for relevant documents. For example, if you have a paper and you want to look for papers that are similar to your paper when you do your related work study. And so the bag of words, how it's originally called in the text mining community, is a technique that reduces those documents to word occurrences, and then based on the distribution of word occurrences identifies similar documents. So basically you say, if I have documents where certain words appear with similar frequencies, those documents are probably similar. And bag of visual words does that concept, but transferred from text documents to images. Also in terms of text documents, so if you know the setup that we use to store our papers, our paper repository, where you have basically the summary of a paper, some images and kind of the title and things like this of the paper, there's a button here, look for similar papers. And if you press that button, what the database will do, it will return you papers, and the returned papers will be similar to the data, to the paper where you pressed that button. And it does so by looking into certain words and simply checks how often do those individual words actually occur in all the documents. And then it builds a distribution of word occurrences over all those papers and will return those papers which are most similar to the one you used as your query. And that's basically the idea of the bag of words approach. And we will now translate that to a bag of visual words. So consider you have an image of an object like this illustration over here. We can actually break down this image into small, let's call them components or small patches or regions or features, and treat those small regions as our words. So for example, we can take this image, we can break it down into small sub-images and keep those sub-images as my bag of words. So as my set of words, counting how often do those parts appear. So for example, here I have a patch which shows the eye of a person, so this eye over here, and maybe this thing actually appears twice approximatively because a person has two eyes, so this would get a count of 2. And other local patches may appear also multiple times, or similar looking patches multiple times in an image. And this I can use in order to generate my distribution. So the first thing I do, I turn my pixel information into visual words. And how Back of Visual Words does this, it uses features and feature descriptors, like those we have discussed here, like SIF features, for example, could be one option to do this. So we break down our image into independent features and then just consider those features in order to represent the image. Here again, these are local patches just as an illustration because it's easier to visualize it in that way. What we also need is to say, okay, which of those words or visual words or image patches or features are actually good for for describing those images. So I kind of need a dictionary. Similar to, let's say, the Oxford English Dictionary, which describes which words are allowed in English language, the visual dictionary tells us which features are allowed for describing those images. So what we need kind of a code book or a visual dictionary which tells us what are the allowed words, what are the words we want to take into account in our approach here. And so they are, let's say, some parts, you can see some of those fraction or sub-images stem from this face example, others include bikes and others may include music instruments, just as a small example. So there's a large variety of words that you need to define in order to have a wide coverage of, let's say, images you can cover. And so you need to have some kind of these dictionaries, and then this dictionary defines the words which will be considered the kind of the allowed words for our comparisons. And then, as I said, I can actually take different images as inputs and then can compute how often do the individual features, so the individual visual words, actually appear in those images. And so this image would have a statistics which look like this image would have a histogram which looks like this, and the music instrument will have a distribution which roughly looks like this. So here we have our visual words, our dictionary words, so all the allowed words, the whole dictionary sits here on the x-axis of the histograms, and the y-axis basically counts how often do those visual words appear in that image. And what the Back of Words approach then does, it simply takes those histograms and basically forgets about the image information and then says, how can I make the decision if two images are similar? And it just does it by comparing those histograms. So you're basically comparing the distribution of visual words that appear in your images. So, and then you will say, okay, if this distribution similar to this distribution, yes or no, with some form of distance metric or similarity. And then you can say, yes, these images are probably similar because their histograms are similar, because their distribution of visual words is similar. And this makes them potentially similar. So that in the end, when querying for similar images in your database, you only need to compare those histograms. And that was kind of a brief summary how Back of Visual Words looks like or operates. So let's dive a little bit deeper into that and see how that works for our data. So let's say the first step is we want to turn the images that we have into those histograms of feature occurrences. So let's say this is an image. This was an image recorded in a car where you had a camera mounted in a car driving around in order to solve visual place recognition tasks. So you want to go drive around with your car on different days, different weather conditions, for example, and you drive through a city, in this example that was in Freiburg, and you are taking images, and when you're there another time, you want to be able to localize in the other database of images. So you take your current camera images, you query your database, do you have images which look similar to the image that I see right now, so that we then can run a place recognition and see, okay, we should be in the same place, then image number, whatever, 128 in my original sequence. And in order to do this, I want to use the Back of Words approach, and the first thing we need to do is we need to turn that image into my histogram of visual words. So again, here on the x-axis of the histogram are the allowed visual words. Now just basically for illustration purposes here shown as different colors, but of course in practice these are unlikely to be color values. And this is the count. So the blue wing would appear 1, 2, 3, 4, 5 times. the red visual word would appear twice, the green one once, and the yellow and the orange one would not appear at all. And kind of this transition from the image to the histogram is the first step that we need to do. So consider, how does it work? We have our original input image, and what we typically do is we extract visual features. And we can run any type of feature descriptor or feature computation that we have in our kind of toolbox. Let's say SIFT features, kind of one of the standard choices for features. So we can run our SIFT feature detector on these images, which computes the key points, so the location where a feature will be computed, and so what's a kind of a locally distinct point, and then the descriptor computed by taking into account the local neighborhood of that key point. So if we run our standard SIFT approach, again this runs on a black-white image, therefore we have black-white here, and we see those circles and those lines over here. And as a reminder, this was the way we were visualizing the key points. So the center of the circle is the key point location. The line over here shows you the orientation of your key point, and the size of the circle was basically telling you at which scale this feature was detected. So these are now the raw SIFT features that are extracted from the image, so locally distinct points. And what we then need to do is we need to reduce those features to visual words. So the reason for this is not every feature will turn into an own visual word, otherwise we would have for every feature detection an own visual word. So the visual words we are considering is just a small number of all potential visual features. So you can see this is every word represents a set of similarly looking features, and they are defined through the dictionary. For a moment, let's assume we have a dictionary, and in a few minutes I will tell you how to compute that dictionary. So that means we take those feature descriptors and we will assign them to the closest word in our dictionary. And maybe we have a maximum distance that we allow for that. Otherwise we say this feature is simply not represented by any visual word. And just for illustration purposes, I now use these red, blue, and green boxes, for example, that we say, in this example, we have 3 visual words which appear. So there's a blue visual word here, here, and here. This is a green visual word, and these are 2 red visual words. And so I'm kind of mapping my SIFT features, or the feature that I've computed, onto those visual words, here just illustrated by a few colored boxes just for illustration purposes. And once I have this assignment, I can actually forget about the image. I don't need to consider the image anymore. So what I can return, I can just say, okay, an image is just something which has visual word occurrences, like this example over here. So again, this doesn't mean that we have those colored boxes over here. It just means that visual words appear in an image, and I don't care about the actual pixel values anymore. I actually can forget them, and I will just continue working with my visual words. And then I'm simply doing counting. So blue appears 1, 2, 3, 4, 5 times. Green appears once, and red appears twice. So it will be the histogram that I've shown for illustration purposes before. Here is my blue visual word, which has a count of 5, red one with a count of 2, green one with a count of 1, and the other 2s did not appear. So we have an histogram 5, 2, 1, 0, 0. So this histogram basically can be expressed by a vector saying 5, 1, 2, 1, 0, 0. And of course here the order matters, and the order is defined through the visual words, and it must be the same for all images. Right? So I can then, with this approach, I can turn every image into a histogram. So in the end, it's a sequence of counts which tell me how often do the individual visual words appear in that single image. And that's how we turn images into such histograms. Okay, in order to do that, what we need our, of course, feature descriptor that we want to use. So let's say SIFT, for example. And we need to define our visual words, our dictionary. So where do the visual words come from? Who tells us which visual words we should use? So again, the dictionary is important in here because it basically is a definition of the words that are allowed, or the visual words that are considered for our comparisons. If we have a feature which is not represented as a visual word in the dictionary, this feature will simply be ignored. It simply will not matter. So the visual word, the visual dictionary and the visual words need to remain fixed because they describe kind of the words we are allowed to use. and they define the x-axis of the histogram. So this is a dictionary. The dictionary is basically, and has an order, say blue is word number 1 in my dictionary, red is word number 2 in my dictionary, green is word number 3 in my dictionary, and so on and so forth. So the allowed visual words and the order in which I consider them in the histograms is defined through the dictionary and is fixed. It's something that should not change. So the dictionary can be learned once. For example, giving a large database, you can build a dictionary out of that for that database. And if you have a very diverse database, very large database, you may come up with a representative dictionary. But this dictionary then needs to remain fixed. You don't change that. And this dictionary, again, is typically learned from data. So it's not something that we specify by hand. We learn that from data. And the question is, how can we actually learn that? So how does that work? So I, in the next few minutes, want to dive a little bit deeper into how I can actually obtain this dictionary of visual words. So let's say we have a training data set. This can be my database I want to work on if this database is fixed, or it can be just a large collection of images taking or showing a large variety of different images in that database. Let's say 1 million of images, and they all are recorded with different cameras from different setups, showing completely different scenes, small objects, large objects, landscape scenes, humans, you name it. And this would be the diverse data set that you could use for learning your dictionary. If you want to apply that to a very specific application like place recognition with images taken from a car in a certain city, then you will of course only take images recorded from a car in a certain city, in this city, under similar conditions, because then you would have a dictionary which is more specific to the task that you actually want to solve. So your training data set should be somehow related to the data set or to the type of data you will be working on later on. The important thing to notice here when I talk about training data set is that this, what we will do in a second, is an unsupervised approach. So you do not need to provide manual labels, for example, for something. It's an unsupervised training or an unsupervised approach where you just need to put in the images and the approach will sort that out on its own. Okay, so how does it work? We take our database of images, let's say those example images here taken from the car dataset, and we extract visual features, for example, SIFT features out of that. So every image will turn into a set of SIFT features. Let's say 500 SIFT features for image number 1, 200 SIFT features for image number 3, 700 for image number 8, and so on and so forth. So we will collect a large set of those SIFT features. So this represents always one single SIFT feature. So we get thousands or 10,000s or 100,000 or millions of those feature vectors, just depending on how many images we have and which parameters we use for our descriptor. So what we have from these thousands or 10,000s or 100,000 of images, we will get a number of SIFT features, let's say roughly 500 times more than images, gives you a good approximation, roughly 500 SIFT features per image, for example. And then you have a large number of those features. And these are not yet visual words, these are just visual features that appear in my training data set. So this is a vector, so in case of SIFT, this can be a 128-dimensional vector, because this is the descriptor that SIFT will generate. If you take other features, descriptors, then they may be of smaller dimensions, let's say 64-dimensional vectors, for example, or 32. That simply depends on what your descriptor returns. And so those vectors are nothing else than data points in some high-dimensional space, in this high-dimensional feature space. So all these vectors are just kind of points in this 128-dimensional space. So I can't visualize a 128-dimensional space well, so let's stick with this, let's say, illustration of a 3-dimensional space, and even that's hard to visualize in 2D. So, but I think you get it. So these are data points which are somewhere stored in this high-dimensional space. Now what we now want to do is we want to actually group similar features together so that they will later on form one visual word. So we take, let's say, those data points which are close together or those data points which are close together and say, okay, this is actually probably very similar image content, because remember, those features just basically provide a description of the local surrounding of the key point, for example, a distribution of gradients or something like this. And so that means we have data points here which represent image regions which show a similar distribution of gradients. You can say, okay, this distribution of gradients, let's turn that into a visual word. And so we can say, okay, those three data points we use and make one visual word out of this, let's say taking the mean of those 3 data points, for example. And we do the same for those over here and for those guys over here. So that we can actually group them here, illustrated by color. This is kind of the red data points. All the red ones are combined together to then form one red visual word, and the same holds for the green ones, for example. And this grouping of similar descriptors is something which is used, or we use a clustering algorithm for that. It clusters our data points in an unsupervised way, or typically in an unsupervised way, so that I then get clusters of those feature descriptors of these points in this high-dimensional feature space, and that I then can find representatives for this. This can either be one feature out of this subset, or what is typically used, a mean feature descriptor vector computed over those data points. So that you basically run a clustering algorithm so that all those data points over here will turn into the blue word, all those guys over here turn into the yellow word, these ones over here into the green word, and so on and so forth. And it's a standard clustering approach that can be used for this. So what is a standard clustering approach? We don't have any special needs in here. The first thing we typically try is something like k-means. So remember, k-means algorithm is a standard approach for clustering. And what does k-means do? Let's give you here a brief few-minute introduction into k-means. What k-means does, it partitions the data that we have, in this case these are our feature descriptors, into k clusters, and we need to provide this k. So we can say k equals 1000 means generate me 1000 clusters from my data set and return me those 1000 so-called centroids, which are kind of the center of mass in the cluster space. So it's basically a mean over my feature descriptors, which are supposed to form one visual word. So the clusters that are generated, these k clusters, will be represented by k centroids, and the centroid is typically the mean of the data points. And then the objective of the k-means algorithm is to find k clusters and assign all the data points that I have in my data set to the closest centroid, to the closest cluster. And I do this in a way so that the squared distances between the individual data points and the centroids to which the data points are assigned to is minimized. So I'm minimizing squared distance. So if we use this k-means approach for learning our dictionary for our bag of visual words approach, that means we partition the feature space, or the feature that occur, into k groups. So we say all the, let's say, 1 million features that we find, we group them into, let's say, 1000 or 10,000 clusters. So k would be equal to 10,000, and I reduce my 1 million data points to these 10,000 centroids, so that always a large number of feature descriptors are assigned to one centroid to form a group. So we have 10,000 groups of features. And then I compute for all the features which have been grouped together into one group, I compute the mean descriptor value, which will be the centroid. And this centroid will be a visual word in my dictionary. So the output of the k-means algorithm are those centroids, are those mean feature descriptors, and they form the individual visual words in my dictionary. And then if I have a feature detection in an image, I will assign this feature to the closest centroid in my dictionary. I say maybe I have a maximum distance that I allow for, and if the feature is too far away from any word, say, okay, I ignore this feature. But otherwise, I will assign it to the closest visual word. So what the k-means approach then does, it generates k words and assigns the features always to the nearest word, and does it in a way that the squared distances between the features and the visual words are actually minimized. So how does k-means work from a technical point of view? So first we could do it informally and then present the algorithm. So we do an initialization. This is typically a random initialization. For example, we randomly sample k data points and say these are our centroids we start with, our initialization of the clusters, and then we will actually revise those centroids. You can choose another initialization, but randomly drawing from your data points is something which is a not too bad starting point. And then what the k-means algorithm does, it repeats until convergence. 2 steps. The first step is assign each data point to the closest centroid. So we have a loop iterating over all our data points and assign them to the closest centroid, and starting with our initialization of the centroids. And this gives me the data association of data points or feature vectors to centroids or visual verts. And then in the second step, I recompute my centroids based on this new data assignment or data association. So I say a centroid, for every centroid, which data points have been assigned to you, and then your new location in the feature space is the mean computed over all, from all the features, and this gives you kind of the new word, the new data point in your high-dimensional feature space that represents the group of features. And then we repeat this approach until convergence. Convergence, for example, can be if the data association doesn't change anymore, also the centroid locations won't change anymore. This can be a little bit tricky in the setup that we will be using here for visual verts. So you typically stop after, let's say, the distances don't really change anymore, or there's an epsilon change in your distances. More formally, the k-means approach, let's say we have m centroids, and xt are our data points, and k are the number of clusters. We iterate over all data points, and then make an assignment saying, this bit tells me which data point t is assigned to which cluster I. So it's I return a 1 in this indicator vector if the distance between the data point and the centroid is the minimum distance. So it means I'm activating this indicator variable b if a data point is assigned to if I found the closest cluster and 0 otherwise. And then this is kind of the step number 1, this assignment step. And this step number 2, which recomputes the mean. I'm basically iterating over all data points, multiply the data points with the indicator variable, and divide it by the sum of the indicator variables for that centroid. And this is basically a weighted mean, although the weights are just 0 and 1. So it's an indicator variable telling you which data point to take into account when recomputing the mean location of the feature. And that's basically it. So just as a small example, two-dimensional feature space. These are my data points, and the red and the blue cross are my initial centroids, which are just random locations here. In this case, they are not part of the feature space, but often you may want to do this. So what do? We first compute our assignment, which is seen over here. So assign all the data points to the closest cluster, which is here shown by colors. So all the red data points will be associated to the red cross. All the blue data points will be associated to the blue cross. And then I'm recomputing the blue cross and the red cross location based on this assignments. So this is kind of the second step of the first iteration. So the new mean location will be over here for the blue data points and the red one over here. And then I again do the next data association. So step 1 in iteration number 2. Then the separating line will be over here. These are all the blue points, these are all the red points. And I'm recomputing the mean. And I'm separating again. You can see now the separation line becomes actually similar. Get the same data points here, compute the separation line. And now the separation line basically doesn't really change anymore. So I say, okay, this is my final result. This is the centroid number 1. This is the centroid number 2. All the blue points belong to centroid number 1. All the red points belong to the centroid number 2. And that's how k-means works. And you can see this as an illustration for having a 2D feature space and we want to find a dictionary of size 2. Then this would be the result that you actually get. Of course, in reality, we have a more high-dimensional feature space, let's say 128-dimensional feature space, and the size of the dictionary is not 2, as in this example, it may be 1,000, 5,000, 10,000, 50,000 maybe, depends on the size of how many images you want to deal with in the end. And but this approach is exactly the same. It doesn't matter if you do this for whatever 100 images, 10,000 or 100,000 images, just that it takes longer, obviously, for larger data sets. So k-means is a standard approach for clustering. It's one of the, or probably the most popular clustering algorithm. It's fairly easy to implement, and the only thing that you need to do is choose your number of clusters, and then give it a run, and k-means will return your centroids. A few things you need to know about k-means if you work with it. First, the initialization matters. So the result that you get depends on your initialization, on your initial centroids, because it iteratively updates them. So it's not a direct solution, it's an iterative solution. So you may want to think about how to initialize your clusters. One example would be to randomly draw data points from the visual features you have detected, and maybe you can have a smart way for kind of distributing the initialization a little bit in feature space, that not everything is clustered in a very local region, which may be suboptimal. The second thing is k-means is sensitive to outliers. If you have outlier data points, so some of the features which are spread very far away from any reasonable cluster in feature space, then k-means may put clusters in those locations, and we have a number of very, very small clusters, a cluster just representing one feature, for example. So one word for one feature. That's something you typically don't want to do. You want to get rid of them. And also k-means just converges to a local minima. It's not a global minima. So these are certain things that we may need to take into account in order to build a meaningful dictionary. But using k-means for this type of approach is kind of the standard choice for turning a large number of feature vectors into a small set of visual words. And k-means is typically the way to go. So what does it mean? We take our database, we just run the k-means algorithm more or less out of the box, and this will actually return me my 1, 2, 3, 4, 5 visual words in this example. And then this dictionary will be fixed. It's not going to be changed anymore. This is kind of a pre-processing step that we do. And then when we run back of words online, so to say, we just stick with our dictionary and say, okay, go, take the dictionary, keep it as fixed, and now work only with that dictionary. That means our database of images will just turn into a database of visual word occurrences. So in this example, we have 4 images. So it's a very small database, and we have 5 visual words, and this is the distribution of visual words, how they appear in the image. And so all of those images are turned into histograms. So we have a histogram for image 1, a histogram for image 2, a histogram for image 3, and a histogram for image number 4. So this would be, for example, the histogram always corresponding to this word. So here we have 5 blue, 2 red, 1 green one, 5, 2, 3. In this example, we have 4 blue ones, no red one, 1 green and 1 yellow one, and no orange one. And here it changes again. So we can see that every image is turned into a histogram. And what is also obvious if you make this transition is, for example, the location of the feature in the image doesn't matter anymore. So it's irrelevant where the word has been detected in the image, as long as it has been detected in the image. So every image is turned into one of those histograms given the dictionary. And again, the dictionary is always the x-axis of the histogram, and the bins, so the height of the bins, tells you how often this visual feature appears. So this means this back of visual words model is actually quite compact summary of the image content. If you think about 5,000 visual words, you basically reduce your image to 5,000 counts, 5,000 numbers, integers, which tell you how often do the visual words actually appear. So it can be a very compact representation of your image. The second thing which is relevant, and this is especially important if you think about place recognition tasks, is that the spatial arrangement of the visual words in the image doesn't matter. So that means even if you change your viewpoint or you rotate your camera or shift your camera, you will basically get the same result as long as you kind of still have see the same object in the scene or a very similar one. So you're largely independent of the viewpoint changes and the deformations. Of course, under the assumption that if you record an image, a scene from 2 different viewpoints, the feature descriptor is also at least to some degree invariant under the viewpoint changes, which holds for SIFT features up to a certain degree. But once you have the visual words, then the back of words approach completely ignores the spatial arrangement and just looks into counts. What's a bit problematic is the question how to choose the size of our dictionary or vocabulary. If it is too small, that means a lot of words are ignored or too many different things are grouped together in one visual word. It doesn't get very expressive. And if you make it too large, basically in the extreme case, every visual feature turns into an own visual word, and this is basically an overfitting to one specific image, and you lose all the generalization, and your performance will also substantially degrade. So you need to be somewhere in the middle. So if you have a small database with a few hundred images, you may want to start with k equals 1,000, and if your database gets much larger, you may want to upgrade it to 10,000 or 20,000 or maybe 30,000 words. But in order to get to something like 100,000 words, you actually need pretty large databases so that this makes actually sense. So what we have so far is kind of the first step. We defined the dictionary and we turned all the images into histograms. So our database now just stores the histograms. So now comes the final step. How do we actually compare image similarities? So how do we find similar images? Either putting in a query image or among the database itself. Let's look here into the example of using a query image. So we have a database and we put in, and we have a search query and say, okay, give me all the images in my database that are similar to my query image. And that's, for example, something that you would do in place recognition tasks. So the task is find similarly looking images. The input is my database of images, my dictionary, so that the database can be turned into my histogram, and a query image or multiple query images. So let's say this is let me by database. I put in one query image, and then the outputs are the n most similar images from my database, similar in the sense of similar to the query image or images. So if this is my query image and this is my database, these may be, let's say, the two most similar ones that I will return. So how do I do this similarity query now? As we said, we don't need to store those images, we just store histograms. So that means that the task of comparing images reduces to the task of comparing histograms. So the question that we need to do, if this the same as this one and the same as this one, or let's say maybe the same is not the right word, but similar one. So how can we compare histograms? And there are different ways how we can actually do this. There are different possibilities how we can compute similarities. Consider this is just a vector of counts. So in this case 5, 2, 1, 0, 0. In this case 4, 0, 1, 1, 0. 1, 2, 1, 0, 0, and so on. So different ways how we can do this. One thing would be the Euclidean distance of two vectors. So we treat those guys as vectors, just counts that we have. And then what we want to do is we want to compute the distance between the histograms as the distance of the data points in a Euclidean space. So this would be a 5-dimensional space here, and this would be 5, 2, 1, 0, 0. So I compare 5, 2, 1, 0, 0 to a data point 4, 0, 1, 1, 0. You just take the Euclidean distance between those 2 points. That would be the Euclidean distance. Another alternative is to take the angle between two vectors into account. So I'm treating those those histograms again as vectors, and then I'm just looking what's the angle between them, what's the angle between those vectors. If there are two vectors which are orthogonal to each other, it's maybe a small distance, and if they look to the same direction, then they may be very similar. So what we typically use this using the so-called cosine distance, where you take the cosine of the angle into account. It's similar to the Euclidean distance if the vectors are normalized, so have norm 1, but otherwise it's not the same or not similar. And again, it turns out in the end that the cosine distance or the angle between the vectors is something again which ignores the lengths of the vectors, while the Euclidean distance is sensitive to the lengths of the vectors. We could also say, wait a moment, these things are actually probability distributions, right? Probability distributions over occurrences, at least if I normalize those histograms. So how do I compare probability distributions? The Kullback-Leibler divergence is one way for comparing probability distributions. So we may want to use this or come up with any other distance metric to use. And so which metric should we use? That's one valid question that we may want to pose. The second thing, which has a very strong impact on the final result, is actually the question, are actually all words that are used expressive? So do they have the same expressiveness? So does the blue word tells me something better or less than the green word or the yellow word, for example? So you can make an analogy to the text mining. Then maybe this effect becomes more obvious. There are a lot of words in language that appear very, very often, but actually do not really help you to classify documents, like an article, like the. The article the will probably appear in every document that you have. And so this word is not very expressive to categorize documents, or the word is, or has, or he, or she, something like this. Probably words which appear in a large number of documents and probably won't tell you a lot about when you look for similar documents. So you may want to say, okay, certain words are less relevant for me and other words are more relevant for me. Okay, so let's make an example and we go back to these 4 images that we had. And if you look, for example, to the green word appears in every image, right? So it appears here, 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 here. So if I get a new image and I say the green word occurs, it doesn't really help me to narrow down that I'm more likely in image number 1 compared to image number 2, because green appears everywhere, right? So the word green is more or less useless for the similarity query that we are doing here. And so the key question is, how can we identify this? How can we say a certain word is better for the comparison and other words are less relevant for our comparison? And so we may want to reweight certain words which are more important and weight other words which are less important down, so that the less important ones don't matter that much when we compare the distances between our histograms. And this is something that we do with a technique which is called TF-IDF. So TF-IDF stands for term frequency, inverse document frequency. And we are basically what we're doing, we are recomputing the bins of our histogram. And what we're doing, we are basically weighting the bins of our histogram with this second term over here, which is the inverse probability that a certain word appears in the database, or an image of the database randomly drawn, and the inverse of this. Okay, so what we're basically doing, we are recomputing the bin of visual word I in image D with this formula. And this gives a new, basically reweights the histograms with the goal that more important words, which are important for the comparisons, get a higher weight, and those which are less important will actually get a lower weight. So let's try to understand a little bit what the formula actually does. So the first part of the equation here, which is this fraction over here, is NID, is the number of occurrences of a word I in an image D. That basically means how often does the visual word I appears in an image. So let's say in our example, in the first image, the blue word occurred 5 times. So for the blue word in image number 1, this would be a 5. And then ND is the number of word occurrences in the image D at all. So for example, if there are overall 8 occurrences of visual words in the first image, this would be then 5 divided by 8. So that's the term frequency. So how often does this term, so how does this word occur? So this is basically our histogram normalized to 1. So this, if you ignore the second part, if you just look to the first expression, this is nothing else than taking the histogram that we have, but normalize them, so turning them into a probability distribution. And then the second term is the inverse document frequency, and I'm weighting this term by the logarithm of the inverse document frequency. So what is the inverse document frequency? The inverse document frequency has here this capital N is the number of images in my database, and I'm dividing it through the number of images in my database where the word I occurs at all. So if, let's say I have 100 images, and in 50 of those images, one visual word occurs. This would be 100 divided by 50, would be 2, so this would be the logarithm of 2. And if you, for example, have a visual word that appears in every image, this would be n divided by n would be 1, logarithm of 1 would be 0. So if I have a visual word that appears in every image, it gets the weight of 0. So the bin will be put to 0 everywhere. So this means this word doesn't matter anymore because it doesn't convey any relevant information for me. And so the maximum you can get is n divided by 1, so you get log of 1. So this is the maximum value that, or maximum weight that a word can get if it just appears in one image. You can say, this is super expressive. This tells me a lot. This is kind of what this is about. So what we can do now is we can reweight all our histograms. So we have to compute this TF-IDF weighting for all our histograms, for the whole database. So I have again here my 4 images in the database. I have the counts 5, 2, 1, 0, 0, 4, 0, 1, 1, 0, 3, 1, 1, 0, 2, 1, 2, 1, 0, 0, for example. These are the histograms, the original histograms, the occurrences that I computed before. So and this is the bin values are my NID, the original bin values. And then ND was the number of occurrences of words in the image. So in image number 0, for example, we have 8 occurrences. Image number 1 has 6 word occurrences, 7 and 4. So it's basically the sum of the individual counts. And then NI was in how many images in the database does the visual word occur. So the blue visual word occurs in all 4 images. The red word appears in 3 words. Green one appears in all 4. The green and the orange, the yellow and the orange one appear just in 1 single image. And this we can use now to compute with this TF-IDF formula all the histograms. Recompute or compute new histograms which take into account this inverse document frequency weighting of the original distribution. So I can now do this. So just an example, here are my images, here are my visual words, and so I can do the computation, the TF-IDF computation here with all the counts, and the green values are our result. And this will turn the histogram for this image into this one. The histogram of this image will be this one. The histogram of this image will be this one. And the histogram of this image will be that one. So I get new histograms, new kind of reweighted histograms. So what the TF-IDF does, for every original histogram, it turns it into a new histogram where all the important words for the comparison will have a higher weight and all the others will get a lower weight. So we are basically changing the weight of those histograms. And those, for example, words which appear in every image will get a weight down to 0. This holds for the blue one and for the green one in this example because they appeared in every image. And the others are advanced, those which occur more rarely. And so this is kind of a reweighting. This is kind of the first thing that I do, saying I only want to take those words into account which actually convey me information for my similarity query. I still haven't answered the question, how do we compare our histograms? Should we take Euclidean distance or the angle or Kullback-Leibler divergence? And as we have now reweighted our histograms, we don't have probability distributions anymore, right? So Kullback-Leibler divergence is probably something we don't want to use because it was intended to compare probability distributions. But we can still ask the question, should we use the Euclidean distance or should we use the angle between the 2 vectors? And it turns out in the back of visual words approach, or back of words in general, people tend to use the cosine distance. So that basically takes into account the angle between the vectors, or the cosine of it, for making the comparisons. We can see that if we normalize our final histograms again, then we can also use the Euclidean distance and we'll give very similar results. But what is the standard choice is the distance based on the angle between them. And what we basically do, we compute something that's called the cosine similarity or the cosine distance. So cosine similarity is the cosine of the angle that is spanned by the individual vectors. So if one histogram is x and the other one is y, then the angle between x and y can be computed in by the normalizing the vectors and then computing the dot product between them. The cosine similarity will give me a value of 1 if the vectors point to the same direction, and the vector of a value of a value of 1 if they point into the same direction, so the vectors are the same, and will give me a value of 0 if they are orthogonal to each other. And this is kind of exactly the other way around that we want to have it. So what we want to have is we want to have a distance. So if we want a distance of 0 means they are identical and larger values are higher distances. Therefore, we take into account so-called cosine distance, which is 1 minus the cosine similarity. Sorry, there's a 1 minus missing here. So 1 minus cosine similarity, that will be the right term. And as long as all the vectors are in the first quadrant, which is the case for us because we're computing them from our histograms, then this will give me values between 0 and 1. So 0 means same distribution, and 1 means a completely different distribution. So what we now can do is we can compute the similarity or the distance between our histograms using this cosine distance. And so let's go back to our example. We had our 4 words, and image number 0 and image number 3 are similar to each other. Right? So they look similar, and so let's see, or there's a similar distribution of features. Let's see if they look similar in our comparison. So what we can do is we can build our kind of a cost matrix or similarity matrix where we have all the histograms of image 0, 1, 2, 3, 0, 1, 2, 3 shown over here. And we are always comparing the difference between the histograms. So this value will be the difference between this histogram and this histogram. And what we can see in here are a few things. So first, all the elements on the main diagonal are 0. This means an image compared to itself has a distance of 0. At least it's a sanity check that everything looks good. Because if you want to compare an image to itself, we should get a distance of 0. But what we also see is that the images of 0 and 3 are regarded as highly similar because they follow the same distribution of visual verts. And as a result of them, they are similar. And all the other values are actually pretty large. They are close to 1. That means those images are very different from each other. They are not similar to each other. You can also visualize it in a plot. You can see here you have your main diagonal with a distance of 0. The off-diagonal elements also with a distance of 0. And all the others are kind of higher values, kind of close to 1 or not exactly 1. And this is kind of our visualization that we say everything which is similar is the main diagonal is identical, and we have the image 0 and 3 which are similar here. And we can actually show, or what we can say is, does it make sense to use actually this TF-IDF weighting, or can we actually do that without? We can do this by performing the same comparison, just using the same distance, also the cosine distance, but on the unweighted histograms. So not using a TF-IDF weighting, just taking the original histograms. And if we compare them, so this is here the original cosine distance of the original histogram, so not without TF-IDF and with TF-IDF. And we can actually see that now the image number 0 and so image 0 and 3 are not similar, although they should be similar actually over here. And here we have zeros in the main diagonal, and the other one is actually some values in between 0.4 and whatever, 0.15 maybe. So this is actually not a good similarity matrix for the comparisons, where this one is a good one. So the TF-IDF actually helps for making your comparisons. Well, we haven't looked into, should we use Euclidean distance or cosine distance? I just said most people use cosine distance. So for that, let's try to identify a bit what's the difference between the Euclidean distance and the cosine distance. So the difference between the Euclidean distance and cosine distance mainly is that the cosine distance ignores the length of the vectors, where the Euclidean distance takes this into account. So if the length of your vectors matters, then you probably tend to use the Euclidean distance. If the length of the vector doesn't really matter, or the distance of the endpoints do not really matter, so the distance of the difference of the two vectors, then cosine distance is probably the metric of your choice. And let's say under the assumption that we have normalized vectors, we can actually show that Euclidean distance and cosine distance are related to each other. We can actually show this here. If we start with the Euclidean distance, or the squared Euclidean distance actually, so Euclidean distance squared, then we can turn this as x minus y transpose times x minus y. And if we expand this expression, we get x transposed x minus 2x transposed y plus y transposed y. And if we now exploit the assumption that both vectors are of length 1, so the length of x is 1, the length of y is 1, we know that their norm is 1. So as a result of this, x transposed x will be 1 and y transposed y will be 1. Sorry, there's a plus. No, sorry, everything's correct. And so this will mean that x transposed x and y transposed y, they will both turn into 1. And x transposed y, this will actually remain. So the equation will simplify into this form. And x transposed y is nothing else than twice the cosine of the angle between the vectors, because remember the vectors have length 1. So this gives me the cosine between them, or twice the cosine, because they're both of length 1. So as a result of this, I will have 2 times the cosine distance. That means if the vectors are normalized to 1, the squared Euclidean distance is equal to 2 times the cosine distance. So there's actually a relationship between the Euclidean distance and cosine distance. And what we can do is we can now make a comparison between the cosine distance and the Euclidean distance to see what's the effect of the different metrics. So again, in this block here, these are the original histograms, the unnormalized histograms. In this example, this is kind of the Euclidean distance and the cosine distance, both executed on the original histograms. And we can see both of them are not very good in finding similarities. So this one is a little bit better. So those elements which are equal here, which should be small values, are smaller than here, but it's still far away from 0. So that's not very good. If we normalize those histograms, then this would be the result. And basically what we have a scaling factor in between them. Actually, this squared would have a scaling factor of 0.5. So also something which is still not good. So this is not the result that we want to have. If we then perform the TF-IDF, we have the thing, our cosine distance that we typically have. And here the distance still looks much different for the Euclidean distance, but you can still see that the results using the reweighted Euclidean gets actually better. And if we then normalize everything to 1, all vectors to 1, just artificially, then we would actually get very, very similar results. So the cost matrices are nearly indistinguishable, not fully, but they don't differ that much because we have just values between 0 and 1. 0 squared stays 0, 1 squared stays 1. So those actually look very similar. So as a result of this, as we don't want to explicitly normalize our histograms, if we would actually normalize all histograms again, we could use the Euclidean distance, but one takes the cosine distance on the reweighted histogram. So I'm computing the TF-IDF and then running the cosine distance on that. This is what the standard back-of-words approach does. So to perform our similarity queries, we use our database and we store the TF, not TD, TF-IDF weighted histograms for all images in the database. And what we then do, if we want to find a similar image, we extract the features from the query image. So we run our SIF detector. We assign every feature that we detected to a visual word, or if it's very far away, ignore it. Then we build the TF-IDF weighting for our histogram. So we need to reweight the histogram. And then we just perform the cosine distance comparison to all images in the database and return the n most similar histograms from our database, or the images corresponding to those histograms. And then I basically get my most similar images. And that's basically it. That's how TF-IDF actually does it. So again, if you want to investigate the back-of-words approach further, there's again this 5-minute summary video of this kind of nearly 1-hour lecture, just condensed into 5 minutes. Of course, we won't go that deep, but the core material is in there. If you want to dive deeper, I actually suggest visiting the Jupyter notebook that was created by Olga Wysocka, who also created all the nice drawings here for me, which you find here under this address, which dives a bit more into the details of the TF-IDF weighting, so that you can actually see how all the individual parts are computed, and you may helps you for understanding the concept a little bit better, and also does some investigations on the different distances. And there is further reading material. There's the original paper by Sivic and Scissorman, which is called Video Google, which had the idea of using the back-of-words approach from the text mining community for image-based data or video data. So this is the original publication from 2003. And if you also want to get some further information about TF-IDF, you may also have, for example, a look to Wikipedia, which can tell you something about this approach. So to sum up, back-of-visual words is an approach to compactly describe images and perform similarity queries between images. And it's frequently used for searching for similar images in a database. This is relevant in computer vision, but a lot for 3D reconstruction tasks or localization tasks, where you want to see what are other images where there are potential correspondencies to my current image, either for finding loop closure candidates in the context of the SLAM problem, or for performing visual place recognition tasks, and then maybe use this as an initial seed for the metric localization system. So there are a lot of applications in robotics and computer visions and photogrammetry for that. The idea of back-of-words is that we base or describe our images with so-called visual words, and we use a dictionary of visual words for making this description. And we are basically just counting how often do the visual words appear in my original images. So how often do typical features which are mapped to visual words actually appear. And based on this word occurrences, or an histogram of word occurrences, we are performing our similarity queries. As some words are more expressive and others are less expressive, we use this TF-IDF reweighting, which kind of enhances the weight of bins or of visual words which are more expressive for the comparison, and weights others down to up to 0, so that they don't matter anymore. And the distance, how it is computed, is basically based on the cosine distance. So we are not taking the images into account anymore, we're just taking the histograms, computing the cosine distance about them. And that's basically it. What you now can do is you can actually sit down and implement that as a small project on your own. So that's actually a very good task which helps you to get an idea on how you want to use the technique that you have learned or to realize a small place recognition system, for example. So the task is to realize your own place recognition system using this back-of-visual words approach. Your input is a database of images, and you have some query images for testing that, and your output is, let's say, returning the 10 most similar images, most not must, 10 similar images given that query image, and you want to implement that, for example, in C++ in order to do this and train your C++ capabilities, and at the same point in time realize a nice small project out of this, where you actually, all the individual components are quite easy and frequently used components like k-means, reading, writing, visual features, building up a histogram, doing some comparisons. So that's actually very easy to do, and I want to encourage you to actually execute this project and train yourself using this technique. A few hints if you want to implement that on your own, you want to dive deeper. So the first thing is, if you extract, for example, your features from using OpenCV, for example, out of your input images, save them as binary files, not as human readable files, because all the rounding issues, if you save float values, for example, as a human readable string, will actually screw up your feature descriptors when you are writing files and reading files again. So use binary files for storing this. Even I'm in general a friend of human readable text files, but in this case, you're better off with using binary files. If you implement your k-means and you do it yourself, first test it on tiny 2D examples you can easily debug. It's very hard to debug something in 128-dimensional space when you directly use these features. And also if your k-means runs on a lower dimensional space with, let's say, 5 different data points, it's very easy to debug and very fast. If you run k-means in general on this high dimensional space with a million feature descriptors, it can be very, very slow. And one of the reasons is you have to perform a lot of similarity, a lot of distance queries. So what's the closest centroid to one of the data points, for example? And this has been done very, very often. This is a slow procedure. And one way to speed this up is not using computing the Euclidean distance to all data points manually within loop iterating over them, but to use a library which is called FLAN for fast approximate nearest neighbor search. It's since OpenCV 2.4, I think, it's part of OpenCV. You can use it, and it's a non-deterministic approach, which is an approximation of nearest neighbor search. So it's very close to giving you the nearest neighbor results, but it's randomized and it's extremely fast and speeds up, let's say, by a factor 100 or 1,000 your k-means implementation. So use FLAN if you work with larger data sets, otherwise that's not going to work out well. You will simply wait too long for your result. And note, however, FLAN is non-deterministic, so if you run FLAN multiple times, you're going to get different results because there's a randomized component in there, which may make it hard for debugging. So you may want to make sure you debug your stuff for small examples first, make sure it works, and then simply replace your distance computation from your manual nearest neighbor search for iterating over all points to something like FLAN. Start with the dictionary size. Let's see, for example, that we provide, let's say, with 1,000, and then you may increase it the more images you take, but don't make it too large, otherwise you will overfit. And if you just take a dictionary size of 10, it's again too small to be expressive. So 1,000 is maybe a good starting point. For visualizing results, it's also quite helpful to not write your own GUI, because you will invest a lot of time in writing the GUI. What you can also do is simply dump a simple HTML file to disk, where you show the query image and show the similar images, because you just need to write a little bit of a text HTML file to disk and open it with your browser and have your visualization more or less for free, so you don't spend much time on that. So if you want to try this, we have a dataset out there which you can download under this URL. This is a dataset that Luciano Spinello and I have been recording years ago in Freiburg, driving around with a car, recording image data, and there's some GPS information in there with timestamp in a file, and timestamp file when the image has been recorded, although the timestamping was not perfect, was just kind of using the computer clock here. And then you have the images from the camera, which are just numbered, and based on the number, if you look up the line in the text file, you find the corresponding data point. So that you have different images, the timestamps and of the individual images, and basically a GPS information of a standard consumer GPS, so you can use it at least for roughly testing if your approach has, let's say, found the right place, in the sense that in the first 10 images you're returning from your database, you actually find a nearby image. And you can use the GPS information just to kind of verify if your results are correct without needing to manually inspect all the images. So if you're, let's say, at the same place in a distance of 50 meters, maybe you can say, okay, we found the same place, and otherwise you failed in finding this. So the next step to realize the project is read the paper, go back to the original sources and read it. Then you may want to dive into the Jupyter notebook, where there are some examples written down in Python how certain elements work here, especially TF-IDF reweighting. And then identify the key components that you want to implement. This will probably be reading, writing files, building a dictionary using k-means, turning your database into histograms, weighted histograms, and then your similarity query. This could be key components. You may create a schedule and assign tasks if you work in a team of 2, and then go ahead, implement it yourself, and you get a better idea on how the stuff works. You actually implement it in your own, and you actually see quite nice results that you should be able, for a lot of situations, to at least find similar places. So if you do it here with us in the course as a student project, you're allowed to work in teams of 2 students. Our constraint is that you should implement all components yourself, just to get coding experience and coordinating the work with your partner. 2 exceptions for these code everything yourself is you're allowed to use OpenCV for reading and writing SIFT features, because we don't want you to implement the SIFT features here. And you are allowed to use the FLUN library for the approximate nearest neighbor search, which is part of OpenCV 2.4 and later. So it's just using OpenCV, you're off. You don't need to have any other libraries. I should say that the bag-of-words approach itself is implemented in OpenCV itself, so you can do it with 3 lines of code if you want to use all functions of OpenCV, but that was not the intention. The intention here was that you actually are able to implement it on your own, so you please use OpenCV only for extracting the SIFT features and using the approximate nearest neighbor search, and the rest should be done on your own, so that you then will get an idea on how that works, and it can be quite rewarding to see the system actually running for yourself. So I hope I gave you an idea on how bag-of-words works, what you can do with it, and gave you some hints if you want to implement it yourself, what to take care of, so that within a rather short amount of time you will be actually able to implement that system. Okay, thank you very much for your attention. I hope you enjoyed the course. Thank you.